what is a conservative force? So you kind of remember what it is, Paul?
I think I know what it is. I just don't know how to say it without saying conservative or like a conservative force.
Did we say in terms of energy,
Yeah.
that the total energy is the same? Like after, if when force acts on it, like afterwards?
Okay. A conservative force conserves energy. I think that's what you're going for.
Like the potential energy and the kinetic energy is the same, even if they change, like the total is the same.
Yeah. In essence, a conservative force will change energy from one form to another, whereas a non-conservative force transfers energy from one object to another. The electric force, is it conservative or not conservative?
Conservative. Conservative.
Yes. So, if a force is conservative, what else is true? Besides energy being conserved. Now, I know there's at least one person here who's heard this before. I think I cut somebody off, sorry.
Does this have to do with potential energy?
Yes?
The equation of potential energy?
Yeah, the fact that it exists.
Yeah.
Every conservative force has a potential energy formula. Therefore, if I take my conservative electric force, so the electric force on one from 2, being K, Q1, Q2, R squared, R2 hat. Since this is a conservative force, there must be a potential energy formula. And thank you for remembering. Now, the work energy relationships. I'll start you out with the work energy theorem, which I think is mislabeled. The total work equals the change in kinetic energy. There's also a formula for conservative, relating conservative work to energy and non-conservative work to energy. So this is
Non-conservative work equals the energy, the total energy,
equals what?
total energy.
You left the key thing out.
The change in.
There we go. Since non-conservative work, I mean, you can think of it this way, non-conservative force, which produces non-conservative work, will change the total amount of energy. It is not conserved. And if you work through it, considering this is the change in kinetic plus change in potential energy, what would this be?
Change in potential.
Plus change in kinetic.
No, negative change in potential.
And we're about to get to the point where we need to start being specific of potential energy, because there is something else that we will come across that is called potential, which is different, but related to potential energy. All right, so these are the relationships right here. So if all I have to do is to figure out the potential energy formula is to figure out what work is being done. So if I have a charge here, Q2, and a charge here, Q1, and Q1 is moving out to here. If I can figure out how much work was done by the conservative force, I can figure out a formula for potential energy. So let's go ahead and label some distances here. We'll call this R1. Let's make R initial, and that R final. All right, another test of your memories. What's the formula for work?
F dot D, right?
The calculus-based formula.
Integral of F?
Pardon?
Integral of FD? Or FDDR?
Yeah. That's
FDR, yeah, integral FDR.
And because there's a dot there, we're dealing with vectors here, so work is defined as the integral of f dot dr from R1 to R2. So as we're looking at this, stop. The force is that's being applied between the two. Let's assume that they're both positive charges. So the force is in that direction, which is the same direction as dr is. Matter of fact, since I'm moving this in the r hat direction, so that would be the r hat direction, I can rewrite this as the work for this problem is the integral of f dot r hat dr from R1 to R2. And that really should not have vector symbols there. That's a mistake. Well, r hat is pointing away from Q2, the force is pointing away from Q2, and so this simplifies into the integral from R1 to R2 of f dr. So just justification for the getting rid of all the vector stuff. Now let's plug in. I have a formula over there. This is a scalar. So it is the integral of k q1 q2 over r squared dr from R1 to R2. Sorry, I suddenly changed it from R initial, R final. R initial, R final. I'm going to pull the constants out, typical calc stuff. Or the form that I personally prefer, just because of the way my mind works, r to the negative 2 dr. And what is that integral equal to?
Look it up.
Like,
I think this is one, I mean, yes, you could look it up. I think this is one that you should be able to do without looking it up.
negative R
Negative
to the power of negative.
Yeah. That was almost insane. That would have been a beautiful thing.
Yeah, Paul and I are like that.
So negative 1 over r initial. Notation's got slide there. And so we're left with plugging that in. We get k q1 q2 negative k1 q2 over r final minus negative k q1 q2 over r initial. Which is equal to k q1 q2 over r initial minus k q1 q2 over r final. That is the work being done by that conservative force. That is the conservative work being done. If our definitions of energy and work are correct, which they have to be because they're definitions, then that should be equal to the negative change in potential energy. So that should be equal to negative U final minus U initial. Or distributing the negative sign, that is equal to U E sub I minus U E sub F. So now the question is, what is a formula for the electric potential energy that would satisfy that? We have that equal to that. So what is a formula for electric potential energy that would make that a true statement?
Electric
Chain board.
Oh, yeah, change in electric force, is that what you're gonna say?
This is over R, not R squared.
The square root of the change it?
Wow, if you're going that route, that was just really bizarre form.
This is something very simple or just.
Yes. All right, so if I said 5 minus 2 is equal to x minus y, what is a value of x and y that would make that true? Okay, what is a formula for, the only difference is our potential energy formulas pretty much have to be the same thing other than the initial and the final parts.
Oh, so just U equals K Q1 Q2 over R, right?
K, Q1, Q2 over
R.
sub R.
Yeah.
That is a formula that works. What is another formula that also will satisfy this?
Negative.
The negative won't work. Oh, it depends on where you're gonna stick that. I assume the negative up front is what you were initially thinking. No, that will not satisfy it.
The one with the E thing.
The one with the E.
Oh, you replace the U with W with work, conservative work.
Conservative work is not potential energy, it's change in potential energy. This piece that you're not thinking of, I asked a question on a test years ago that had a really simple answer, but no one got it. Because they forgot this one thing.
So what are you asking again?
Another formula for potential energy that would satisfy that equation over there. There are an infinite number of equations that work. You've got one of them.
And it doesn't have to do with the integral.
No, nothing special about the integral. No, we're past the integral part. It comes straight down to what can I make use of E so that the initial minus the final gives me that. Delta.
And it's not KQ1, Q2 times like 1 over Ri minus R. So,
All right. Since this is a change here, a change in potential energy, and I mean, you've got the base, that's the major part right there, but there's another little piece that is really convenient for some of the stuff that we're gonna be doing. If there's anything else, it would have to somehow cancel out. Whatever it is would have to somehow disappear so that we still get this. In other words, if this were +1, the ones would cancel out, so this is still valid. Or in general,
Let's see.
or whatever letter you're gonna use for constant. It's just that formula plus some constant. Oh, that's an incredibly important concept there, because we don't know what the actual formula for potential energy is until we introduce something else. All we need to do, all this tells us, all the math tells us is what the formula for change of potential energy is. And then from that, we make some assumptions. Now, what this allows us to do is it allows us to set zero wherever we want. And so that simple problem I asked on the test is I gave them a sphere with a charge and I said the potential energy at the surface is this, and I gave it to them, or probably electric potential, and I said, explain how that could be. And people would jump through hoops because they always made the assumption that this constant was zero. And if the constant is zero, then yes, my statement was impossible. But I can set zero wherever I want. Because what really matters is not the actual potential energy, but how the potential energy changes.
Still lost.
If I have an object going from here to falling, let's just use gravitational potential energy, mgh. Got the ground here. This is, let's say, 20 meters, and this is 5 meters. It starts at rest, so K initial is 0. If I want to figure out, use energy to figure out how fast it's going at this point, would you do, I got 1/2 mv initial squared plus 1/2, no, plus mgh initial equals 1/2 mv final squared plus mgh final. I assume you would at least use the energy to do that. Mass cancels out. And this is 0 because it said it started at rest. So I'm left with gh initial is equal to 1/2 vf squared plus gh final. Someday, I just had this idea of coming in here and raising all the boards.
Yeah. Looks like it's possible too.
Yeah,
If they wanted to do it.
In the classroom on the end upstairs, the maintenance took the boards down to do something and they put it back up at a much higher level. So the Sasa couldn't reach the top. Oh, well, that was a consequence. I don't think that's why they did it. Now, so if I wanted to figure out how fast it's going, I've got 1/2 vf squared is equal to gh final minus gh initial. What would you plug in for hi and hf?
Whatever you want.
Well, there are some limitations.
GHI minus GHF.
You know, I mean, well, you end up with g times hf minus hi.
Is it HF 0?
Pardon?
Is it HF 0?
Sure, why not? Or,
Could be 2 meters.
Each initial is 0.
yeah, I mean, you have to establish 0 somewhere because the actual values of the height are irrelevant. I have this thing falling 15 meters. The ground's 5 meters below that. The ground could be 10 meters below that. That doesn't change the answer. How far it is from the ground is irrelevant. So the formula for gravitational potential energy, where G is relatively constant, is that plus something, some constant. And it allows us to make the potential energy equal to 0 wherever we want. The same thing here. This is what the constant allows us to do. Now, traditionally, textbooks at this point will then go, well, if R equals infinity, the potential energy equals 0, that will establish the constant. We're establishing, because if R is infinite, this fraction here goes to 0. If that's 0, the constant is 0. So that condition right there makes the constant equal to 0. And that is traditionally how people look at it. They present the simpler formula of it, just like over here. Although, oftentimes, they'll just establish we can make 0 anywhere we want it to be. It doesn't have to be the ground. But it comes from the fact that we can always add a constant, and the change in potential energy is the same.
So has this concept been around even like during all our kinematics work too? We just decided to like ignore it, they didn't introduce it until now?
That constant, there is a certain aspect, because displacement,
Like even what you were doing with kinetic energy and stuff, it's just like they chose now to introduce it, or does this only specifically relate to potential energy and electric force?
It is very similar to the idea of, I can make, in kinematics, I can make the origin anywhere I want it to be. Or I can make displacement relative to the starting point. It doesn't have, I don't have to know what position I'm in order to solve most of the problems from 251. I just need to know where I am relative to where I started. It's similar to that.
Okay.
All right, now the next part, because we've explained why opposites attract and like repels using force and using the electric field. Now we get to do it with energy. So if I have a charge here, Q1, and a charge here, Q2, if they are the same sign, which direction will if Q1 already exists there, I put Q2 right there. Which way will Q2 be forced?
Positive I hat.
I'm gonna nitpick that. Probably 152, I just let it go, but 252, I'm gonna nitpick that. What's wrong with what Ibrahim just said?
We don't know where the I hat is.
We haven't defined it yet. Okay. I assume you wanna make that way I hat based upon
Yes.
your gesture,
Wait, can we actually make it J this time?
make it J hat?
Why?
Just make it wrong?
He likes making things harder.
So it is gonna be moving in that direction. So the distance between them, R, will be getting larger. I know that if I put Q2 at rest and then it starts to move, it will gain kinetic energy. It is redundant to say if something is at rest and then speeds up, it is redundant to say that, well, actually, that's redundant. You could just say it starts at rest and it moves. It has to speed up. And I've had plenty of students this semester who have to emphasize that it started at rest and then it sped up. Okay, not wrong. All right, so it starts here at rest in my scenario. It starts to move, so kinetic energy increases. It's a conservative